Very good morning, all. So, welcome back to the class, and I'm sure all of you are well prepared now to discuss the implementation aspect of MST, that is minimum spanning tree algorithms. MST implementation, we are, as discussed last time, was related to Prim's and Kestrel's algorithm. For Prim's Kruskal algorithm, we already said that we need the concept of a disjoint sets. So you require the disjoint sets and forest, etc., to be used. And in Coreman, the details are given. So read Coreman book also and have a clear understanding of their storage of disjoint sets. So read and try to implement. That is, those who are good students, they must at least try this immediately. Otherwise, later, of course, you will be learning this. Next semester, you will be studying in more detail also. And if time permits, sometimes later, I'll give brief discussion on that. But today, we are going to see at Prim's algorithms implementation and the corresponding analysis. And for that now, whatever discussions we do, that is going to be crucial and very useful for the future discussions on the graph algorithms like De Castre algorithm and shortest path algorithms, etc. So be careful, have a clear understanding. And now today we are going to make it as a formal modular, no global variables, everything with good concept, good structuring, and all those things to be done. It will also require some modifications into our previous data structures chosen. So we will be discussing all that. So today we are going to talk of very important discussions, and be careful and understand that. So we are going to have a total detailed analysis done today. Well, when we talk of all this, first we will recall how Prim's algorithm was working, and then we will be able to go to that. So let's go to and talk on that. Let's say I have a graph with me. So I have this graph with me available for discussions. I will start from this graph, and we will just recall how my Prim's algorithm was working. So let's assume we needed to start from a source vertex. So source vertex needs to be known in case of a Prim's algorithm. Assume, let's say, node 5, vertex 5. So vertex 5 is a source. So I say, this is my source vertex. So effectively what I said last time was that we will start from 5, and slowly after 5, the minimum weight edge out of 5 will be used to connect 5 to other uncovered. So what our logic effectively said was, initially my answer set is empty. Answer set, or I have not selected anyone. Empty, I'll say 5. Then source gets selected and source goes to answer set. Answer set. So effectively, my uncovered vertices initially, except the source, will be, let's say, 1, 2, 3, 4, 6 will 5 will go there. So I say 6. And my answer set initially was empty, and later I got 5 as a source. So last time I gave a hint that now effectively what I need is one of the uncovered vertices is supposed to go from this side towards answer set in a way that we are going to select the vertex. I say my basic aim was select an uncovered vertex which has minimum weight connection, to covered, to any of the covered vertex, to any vertex in the answer set. This one line effectively explains everything, and this process will be repeated every time. This will be looped. So first time I say 5 is already there. Effectively, what I see in this case is out of these, what connected with 5 are 6, 4, and 2. So out of these, now one of them will get selected. Obviously, corresponding to this, I can see 3 is the minimum weight. So 2 was going to come. So going more systematically, I will say that all these uncovered vertices need to know that which is their minimum weight edge towards answer set, which is there individually, which is its, I'll say, minimum weight edge to a vertex in the answer set. So if it needs to know, and accordingly, I'll say out of this, 2 has got a minimum vertex connection with weight 3. 3 has, then 4 has got minimum connection towards answer set with weight 4. And 6 has got connection towards that answer set with weight 5. Obviously, 2 will get selected. So then my answer set will become 5 and 2. Now, based on this, I will say uncovered vertices are 1, 3, 4, and 6. And they also need to know minimum weight edge connection towards this. And we will find again similar and proceed like this. So this was how Prim's algo was working. Now, let's go towards its logic development and implementation, and then I'll be again coming to this back. So now we proceed to plan the implementation. First thing, we require weights to be stored of each edge. So, and many more things. So effectively now storage, or I'll say data structures for the corresponding graph, we are going to redefine. To be redefined or to be improved. Because now there are other things. Earlier, what we have taken was nothing but we had a graph as array of pointers, simply array of pointers. And here I had, let's say if I'm talking of vertex 5 itself, for vertex 5, I had its a connection to 2, I had its a connection to 4, I had its a connection to 6, but weights were not stored. Now we need to take care of all things. Also, we need to take care of how to store the key or priority queue. That also is to be seen. We also need the parent also to be stored, etc., etc. So parent will be vertex via through which this vertex is covered. Through which this vertex is reached or connected. So that way we are going to use in MST. So all these things needs to be stored, hence storage needs to be redefined. So let's go one by one. First of all, I already know that weight needs to be stored. Weight is stored for each edge, so related to edge, not to vertex. So effectively that means my edge structure needs to be modified. Earlier, which was my edge structure, for each edge, I had one node like this. Now, this is not sufficient. Along with this, I have to store the weight also. So what I effectively need is that I am going to have correspondingly, like if I have earlier said, with 5, I had 2 at weight 3 and 4 at weight 4. So I can see this was this one connection, this is another connection, this is another. So we will have effectively this to be, now what we need is that this should be 2 as a vertex and weight as a 3. So this was my vertex. Then I need, say, 4 to be stored with weight as, let's say, 4 itself. By the way, I think we had the weight as 4 only. Let's check. Yes, 4 is 4. So for vertex 5, I am talking of. With vertex 5, this is the adjacency list. And then similarly, I have vertex 6 connected with weight 5 and 9. So I need now this. This is weight. That means my edge node will be revised. So I will say struct. I will call this node as an edge node, because we will have another node which we will call as a vertex node. In this earlier, I have stored vertex. That is perfect. But now I also need to store weight. And of course, a next pointer. So next pointer is going to be of the same node type. So I'll say struct edge node star next. So this is the same structure, and this becomes effectively the next pointer. So now I have these 3 fields. That becomes 1. Secondly, for now we also need to store the parent of a vertex. That means it's a property of a vertex. So that means for each vertex also, I just don't need only their index, I need their parent. Secondly, I will also need to know, is vertex covered or not? Or not. So that means vertex structure also needs to be modified. Vertex property. So I am going to make vertex to be modified. So earlier I had no information about the vertex except its index number, and that was indirectly in the array itself used, nowhere stored. But now we need some additional info. So for each vertex, effectively, I need something more. What I need? I'll say I need a parent to be stored. So for each vertex, what I need is parent to be stored. I will say I need one in covered vertex or not. So I will call it as an in PQ or not. It's a flag or Boolean flag, which will tell whether this vertex is in the priority queue or not, as we have seen that priority queue we are going to use. So flag will tell whether it is uncovered. In priority queue will mean it is currently uncovered. So what we earlier said that this is my uncovered, I will say all these vertices will remain in a priority queue. In a priority queue, which is of course a min heap or min priority queue. So it is a min PQ. So these all vertices will reside in PQ, and whenever we are going to find the weight, etc., to be adjusted, key, etc., to be adjusted, we need to know whether the priority, whether this vertex is covered or not, whether this vertex is still in PQ or not. So for each vertex, that information needed, I am going to this. Another field I am going to use later, I am not writing at present, but we will need, so I'll just leave it open. And then I need a pointer to adjacency list, so that I have here, let's say, edge corresponding to connection with 2, edge corresponding to connection with 4, edge corresponding to connection with node 6, as we have already. So these are the edges, effectively the same which we have above done. And this pointer, earlier we were using only this pointer in each vertex. So now I'll say, let's say I call this field as adjacency list pointer. Adjacency list pointer. So that means my structure for the parent also changes. So I say, effectively now I will declare struct parent node or vertex node, sorry, structure for the vertex also changes. So I have struct vertex node. In this, what I'm going to store? Parent. I'm also going to store a Boolean variable. Boolean I am writing, so either you can write int also, but it will help you in remembering that we are storing whether it is inside PQ or not, true or false only. So it's a Boolean variable. Another field I will use later, but then I need another pointer, which is known as adjacency list PTR. And this is going to point to what type of data structure? This is going to point to edges, that is edge limit. Earlier also, we had only one structure, node, and then this was a pointer to that node. Now I have vertex node separate. So for vertex, this connection becomes. And effectively, earlier, I had array of pointers, array of adjacency list pointers, lot of pointers like this. Now I will use array of vertices. They have the pointers plus additional fields. So I'll say this is going to be my graph. Earlier, my graph was simply pointers storage, but now my graph has vertex 0, vertex 1, and so and so. Let's say 50. So 0 I will not use, so that we are simply using 1 to n, but this all each has an adjacency list. But along with the adjacency list, it has 3 other fields: the parent, the in PQ, one more field, and this. That indirectly means now I need to declare my graph. So I need to declare my graph as an array of 51 elements. 0 I am leaving empty, so 51 I am using here. And what is the type? The type is now obviously, yes, you can understand, it is going to be vertex node. So now my vertex node type graph is declared. So this becomes my graph. And in this, the one significant point to be taken care is that whenever you have to refer to any field of this structure, you will use a dot. For example, graph I dot parent, graph I dot in PQ, graph I dot ADJ list pointer. Remember, it is dot field. You will not use here arrow. Arrow you use only when you use pointer declaration. If something was declared as a star graph, only then star graph something, only then the syntax will be graph I arrow something. So this arrow is connected directly with use of a graph star here. We have not used a star here, so we will be using dot while referring to this. So having said that, this is clear, I hope, by now. Then comes, we require a priority queue. So we have to decide how to store priority queue also. We said all vertices. So I say now, all vertices are initially uncovered and they will be in the PQ always. Initially. Later, all say, so what will happen? One vertex will be selected, removed will be selected, I'll say, or I'll say not selected, I'll say extract word will be a better word, will be extracted from PQ, as we did just let, extracted from PQ, and taken to answer set. So this process will be repeated many times. How we will extract, we know, we have discussed based on minimum weightage, that I'll talk, but effectively it means PQ will all times will have set of vertices which are not yet in the answer set. Set of vertices not in the answer set. So effectively, I mean, PQ is going to be a array, min heap, whatever you say, of vertices. So accordingly, I have to declare its data structures. And we will be using all PQ coding. PQ coding we have already done, that will be effectively reused mostly. In a way we are implementing. So we need that. Obviously, when we are saying PQ, so we will have here struct, let's say PQ node declared, within which one will be obviously the vertex, which we will be storing. And the other field is going to be the corresponding key on basis of which priority will be implemented. Effectively, key is equal to minimum weight corresponding to this vertex. So what I say, what key will store, key is equivalent to, I'll say one line, it is going to store minimum weight out of all edges connecting this vertex to vertex, to any vertex in answer set. Obviously, there can be many connections, so this will be helpful to me to maintain the corresponding minimum weightage. And out of all minimum weight vertices, one vertex which has overall minimum weight, that will get selected and that will be getting extracted. So I said extraction will be based on this key. So this key should maintain for each vertex its possible connections with answer set. And out of multiple connections, we should store the minimum weight connection. So effectively, I need this as a PQ. Of course, this is one node. I need an array. So I will declare PQ as array of PQ nodes. And I'll say PQ, let's say 51. So I have again 51, assuming maximum 50 vertices. So PQ is also array of vertices. So these are three data structures we will need: edge node, vertex node, and PQ as array. So graph is array of vertices. PQ is also array of vertices, but here vertices have also the weight. In graph, vertices also have the parent in PQ flag and one more field along with adjacency list. Knowing this, now let's go and understand how we are going to use all this towards programming. Just 5 minutes we will use over the same example, and then coding will be very simple. Let me just have the same graph reused for you. So I'll just copy paste the same graph once again. I have stored this graph already. So I'll just paste it here and resume. Yeah. So now I have, let's say, using this data structure, which we have just recently discussed. So I will say PQ initially. So I will have my graph where I will say graph has initially parent. It also has in PQ, it has some more field and a connection. So correspondingly, everywhere those connections. And for vertex 5, let's say, for example, I know that this has got a connection to vertex 2 with weight 3 and so on. So first I will say PQ will initially have my vertices 1, 2, 3, 4, 5, 6. This will be available as a PQ. These are the vertex numbers, and I have the corresponding key. So key I show here. Initially, I will make a key as infinity for every node, meaning that no edge exists from this vertex to answer set, to answer set vertices. If there is no connection available, this will remain infinite. Initially, nothing is in answer set, so no connection exists. Everybody will have infinity, obviously. Then what I'm going to select source as starting point. So source will mean 5 will be selected. So 5 selected means this will be there and I will make its key to be 0. Why I am making 0? That key equal to 0 will help it to come on the min heap top. It will come on the top of the PQ after heapify or build heap and will be extracted automatically every time, will be extracted first time, and later, of course, we can do. So first time, I want source to come out of the heap, so I will make its key as 0, and others are undisturbed. Having said that, good enough. Then I have to also see 5's parent. 5 is being covered via no one, so I will say 5's parent will remain -1. So everybody will initially have -1, and whenever somebody is reached via certain vertex, parent will be updated. So 5's vertex, 5's parent will be here initialized to -1. Initially, everyone can be -1, but 5's vertex parent will guaranteedly remain -1. Initially, everyone is in PQ, so every vertex has in PQ status as 1. Later, this will keep on changing, and like that. So this 5 now. So 5 is gone. Automatically, 5 will be extracted, and extracted means it will go out of a PQ. Of course, a PQ will have that extract min and array adjustment, and this wall shifting, etc. Indexes changes, and all these going. But logically, all these vertices are inside this, and answer set has a 5. Now comes the important step through which the whole logic will work. We said key is supposed to be updated, updation of the key to be done for all these vertices. For which vertices? Which are in PQ, keys of vertices in PQ. Obviously, how to update? I say corresponding to 5, I have connections towards 2. That is one connection. I have this another. Sorry, let me correct this. I have this as I have this another connection, and I have this another connection. So 3 connections out of 5. That means now vertex 2 is reachable out of a PQ towards answer set. Earlier 2 is not reachable, but now 2 is reachable, and the key is to be improved from infinity to 3. This similarly, vertex 4 earlier had as an infinity connection. Now infinity will be modified because the 4 is reachable to answer set via 5 with weight 4. We can see this. So similarly, 6 is also reachable to answer set, and 6 has got a connection. Earlier 6 had no connection, so 6 has got a connection, and this will be reachable to this particular value via this particular 5 with weight 5. So keys are updated to this. So this 5 is this value, and like that. So after this, again, after this, now again, they will be heapify, or I'll say effectively again heap adjusted. So heap adjusted, PQ adjusted. Obviously, vertex 2 will reach on the top, comes to top. So 2 will be extracted. Extracted will mean the answer set will get one more vertex. Extraction should also mean the corresponding in PQ to change. So vertex 5 was taken out. I should make this as 0, not in PQ. After this vertex, let's say 2 will be taken out. So 2 will be taken out and 2 will be later said to become this. And now 2 has come, so 2 will be out of this. 2 will be out of this PQ. And now we have to again update this process. Update keys of vertices in PQ. So keys of 1, 3, 4, 6 might require updation. All might not require. Who will require updation? Updation will require the vertices which are adjacent to 2. Others will unchanged. So 2 has adjacent as 1 via this. 2 has adjacent 6 via this. 2 has adjacent 3 via this. So I'm going to look upon these 3 one by one. Let's say 2 to 1. 1 is already in PQ. So 1's key is definitely to be considered. 1 is in PQ. Current key is infinity. Now 1 is reachable via 2 to the answer set. So next time vertex 1 can be possibly used and this key will become 6 because using this 2-1 edge, if vertex 1 gets selected, it can go to the answer set because the 2 is already in the answer set. So next time 2's adjacent can also go and it will still satisfy the Prim's logic. So that can be one way. Now I am not have this. Then secondly, 2 versus 6. 2 is connected to 6. 6 is also in PQ. So I'm going to update 2's connections or 6 connection also. 6 current weight is 5. With 2, the weight comes to be 1. So it will be better if 6 is reached via vertex 2 than vertex 3. Than vertex 5. So vertex 6 was being reached earlier via this, which is not preferable now from vertex 2 viewpoint. So I will say vertex 6 viewpoint. So vertex 6 is now reachable via vertex 2 with weight 1. Earlier 6 was 5. Now this key will be decreased to 1. Decreasing, of course, will mean heap adjustment, but this will also help in making 6 now reachable. So 6 parent will also now be considered as vertex 2 and 6 key also updated. Similarly, then 2 has another connection, which is connection to vertex 3. So 3 will be also infinity. This will get improved to 8. Not only that, 2 has also a connection to vertex 4. 4 is also in PQ. So 4's key also to be considered. Via 2, the weight is 7. Previous key of the weight of 4 is already 4. Previous key is lesser. So there is no need to go to vertex 4 via 7. Hence, this will not be changed because the new weight is more than the previous key. So nothing to be done. Remembering this, so effectively I say key represents effectively the minimum weight edge. So I recall again that key was nothing but minimum weight out of, I'll say minimum weight out of all edges connecting this vertex, connecting it to a vertex in answer set. So after second iteration, you see vertex 1 is reachable with weight or minimum weight 6. Vertex 3 is also reachable with minimum weight 8. Vertex 2 is at present already in this. So not in this. Vertex 4 is also reachable with weight 4. Vertex 6 is reachable with weight 1. And answer set 5 has 5 and 2. Earlier answer set has only 5. Some vertices were not reachable or not possibly considerable and like. Out of this, again now, the minimum one will be selected. So next iteration, 6 will get selected, vertex 6 tree will be extracted, and the process will be repeated. Knowing this, the coding becomes very easy now. So I can easily write the code without much difficulty. I say void prim mst, whatever you require here, minimum source needs to be informed along with other parameters. Source is obviously needed and we need that. So now the logic is very simple, only 4 or 5 steps mainly, hardly 7-8 lines code. First step, we have to initialize my all vertices, etc. So effectively initialize parent and in PQ, etc. Etc. I am writing because later I am going to use another field. Effectively, if it means for all I will write graph I dot parent to be initialized, say as -1, and dot in PQ to be initialized with, let's say, 1. Initially in PQ, it means initially in PQ. Everybody is initially in PQ. So initially every vertex is in PQ. So initialize the parent in PQ, etc. That is one step. Second step, PQ also to be initialized so that later PQ can be adjusted, because PQ initialization will require the vertex and keys to be initialized. So effectively for all I, this also to be done in PQ array. PQ array dot PQ dot vertex to be given equal to what? Currently, each vertex is nothing but the I itself. Later, of course, these vertex number will remain same, but their position will keep on changing. Their index will change. Initially, I am saying we are initializing your array 1 to n. Later, of course, they will keep on swapping, and based on key value, they will be adjusted. Initially, everybody has the key taken as infinity. So some bigger in a max int or int max you can take, and done like this. Then going to step 3, source based step start. So you have to start source based. Effectively mean that I have to say that from source I start. So source based will mean in PQ, currently source is guaranteedly at index source. So I can say its a key to be made as 0 so that it will become on the top of the heap. So my source based initial starting done and key is initialized and the process starts. The advantage of this is after this source vertex should reach on the top of the PQ. How it will reach? My PQ is currently only initialized. I have not heapified it. So first step to adjust my array to become a PQ is we always called build min heap. So build min heap over PQ will be called, and this will automatically adjust. And obviously the root will become the corresponding source node. Source and key as 0, and rest all will be effectively available at. So this will become at index 1, it will reach at index 2, 3 onwards. All other nodes will be there as per their property, and all others have infinity value. So all others will lie at some position. So ideally, this build min heap could have been done easily by adjusting for min heapify for source because all others have same value. But this is a standard operation. So I use build min heap to claim that every time heapification first time is needed overall over the total array, and later only extraction, etc. done. So already implemented, we are going to reuse the code effectively. The whole code will be reusable. The code is already implemented. Now what we have to do? I have to effectively loop. Effectively loop means either n times, or you can say while PQ is not empty. Because PQ has exactly n vertices, is not empty. You have to repeat. So either way you say, what I have to do? Every time the process we said was, just recall, every time what we have to do is extract the corresponding process. So every time one vertex will be extracted and taken to answer set. And after that, what we are going to do, update keys for the vertices in the PQ. So only these two steps mainly. So that means I extract min. Extract min, again, we have a standard operation available. Reuse that. So extract min from PQ. So code reusable. We have already implemented. Let's assume this is always called as a source vertex U. And as we have already said that we will use a nomenclature UV. This is your source vertex, initial vertex, and this is your others are going to be its adjacent vertices. So UV extracted. Now, based on the U, once we have extracted this, it goes to answer set. So answer set to be updated. You choose your suitable data structure. I am not saying how to do. I'll just explain later and include U here in some way. Include U and what else, etc. Edges, etc. Corresponding edges, edge if at all. Edge also. In this case, U is first time empty, but the corresponding edge also, if you need, yeah, corresponding parent also. Whatever you want to store in answer set, that you will do. Later, I'll tell what to do, but this is not an important point at present. U is extracted. Now what we have to do? Let's recall what we did here. As soon as I extracted 5, adjacent of 5 were used to update the key if they were in PQ. Adjacents of 5. Later, I extracted 2, and then I said adjacent of 2 to be updated. So effectively, I need adjacents of U. Obviously, adjacents of U are available with, I can say, temp. So I'll say, where are the adjacents available corresponding to vertex U? They are available in the graph U. U is the index in the graph dot adjacency list pointer. Dot still. So this becomes effectively corresponding to vertex 5. This was vertex 5. And this is, say I have 2 with weight 3 and all connections. So this is my adjacency list pointer. So I got a template. So obviously all adjacents are to be covered. So I will say while temp not equal to null. What to do? If the adjacent vertex is in PQ, then its status is, or its key is, its weight is to be checked if it is in PQ. So which vertex? Adjacent vertex. Means I'm talking of vertex 2. How to find this? Let's say it is called as V. So V is nothing but temp arrow vertex. This 2. Now, is this 2 in PQ or not? I have to check. How to check? We have in PQ status. So I can say if graph of V dot PQ or in PQ equal to 1, it means it is inside the PQ. If it is not, nothing to be done. We will go further. If it is inside PQ, that becomes one thing. And if the key is current weight is lesser than the present key, the key is to be changed. Yeah, decrease key. So I want to effectively call here decrease key. Means if the key is currently higher, say current key is infinity, Initially for vertex 2 key was infinity, I have to update. How to check? I want to say whether this current weight is less than the key of vertex 2. This weight is less than this. How to find this 3? So this 3 is nothing but temp arrow weight. Temp is pointing to this node. This is my temp. So I say temp arrow weight to be less than whom? I say less than key of V in PQ. I am not writing the syntax. We will just see why. But I'm saying corresponding key of P, this vertex V, I'm talking of this vertex. If this weight is less, obviously I have to decrease key to be called, because weight will be, or key will be updated. So how it will be updated? It will be updated with new value. So decrease key, again, reuse code we have already written. So reuse this. So in reuse, effectively I used to tell for decrease key the index to be told and new key to be told. These to be told as a parameter. Index, I say index of V to be told, and the corresponding new key. New key is definitely temp arrow weight. Index is not V itself. That is why I am writing here only index. We will see how to find. So index of V, because in PQ, indexes will keep on changing based on priority queue and based on key. So if vertex number is a 5, it might not be at position 5 in PQ. In graph array, it will be at index 5, but not in PQ. PQ position changes. So I need to know that. But once decrease key done, effectively more or less my logic is over. The only thing remaining, what to do updation for the parent and where to do. We have not touched the parent yet. So yes, where to touch parent? Whenever parent changes, whenever you get a better parent with a lesser weight, you are going to change the parent. Till now, there was no parent available. We had infinity. Now parent has come. Whose parent has come? Effectively at this stage, V's parent is becoming U. Becomes U now. So V's parent will become U here because V's weight is updated. V's weight is being updated. So V's parent is changing. Where to store? It is in the graph. It is in the vertex. So directly that position is available. So I can update graph V's parent to become U. And like that, maybe after that you have to change temp. So temp equal to temp arrow next to be done, etc. etc. More or less logic done. Another thing worth to see, have we updated in PQ somewhere? No. Ultimately, we need to check, and this should go somewhere 0. So we have not changed. This is somewhere. So how to change this? Where to change? Obviously, when it comes out of a PQ, it should be changed and it should be made as 0. Where it is coming out of PQ? Here. That means after this, I can write graph U dot in PQ to become 0. Because now it has been extracted. So next time it should not get used at all for any other node. So this will be updated. So this becomes more or less logic over. Effectively, what I have done is for every adjacent vertex of extracted vertex, for every adjacent vertex of extracted vertex, or for full adjacency list of extracted vertex U, I will check if V is inside PQ yet and V's weight is current edge weight is lesser than the previous key. I am going to improve or adjust the key, decrease the key. make the T key to be lesser so that it will be used. After this, automatically decrease key will automatically heapify also. So that will be automatically heapifying, and out of this, all those will automatically adjust. So that will all be taken care without much of a problem. The only question remains how to find key. So coming to last discussion, how to find key of, how to find index, or I'll say index of V in PQ. Because this will be used at two stages. One is your key of V to be used. And secondly, in a decrease key also index needed. So index needed at two places. This becomes place 1, this becomes place 2. So how to find index? Obviously now there is a question. You cannot write PQV itself as index. No, this is incorrect. You can't say PQV dot key because V is the vertex, that is fine, but at index V, this vertex might not exist after certain iterations. Index V is the vertex, but index might change. Index keeps on changing. You swap so many things, vertex will go somewhere else. So one way, solution 1, search linearly. Search linearly how? I will say effectively with what I can say is for I equal to 1, I less than equal to n, I plus plus, and say if PQI dot vertex equal to V, because vertex number is stored with each index or each PQ node, so I can compare. Then I can say PQ index equal to I. So I say I need something known as a PQ index. This I name variable as PQ index. So this index I claim to be called as PQ index. So this PQ index I can find like this. Yes, okay, but additional time complexity. This will have extra time complexity of order of V. Because every time this needs to be searched and this becomes extra time. Not a desirable. So a better solution. That we should do it in order of 1, not order of n, not order of V. How? So I say solution 2. We will store PQ index also in your vertex node. For each vertex, the vertex node is available, and keep on updating PQ index whenever swap or whenever some swap happens in heap. So I say whenever changed, whenever index is changed, indirectly meaning internally inside the PQ or heap, I'll say inside the PQ or heap, whenever swap happens, this will be done. So this you can just add 1 or 2 lines in your corresponding functions in the reused code. In the reused code of your heap of PQ oblique. So whatever functions you have used, in that this you need to take care, but the advantage will be this PQ index will be directly available. So for vertex V, I can always say my PQ index will also be stored, and my vertex structure earlier, if you remember, I said it had a parent, it has in PQ, and then I had left one place. So this I will use as a PQ index, and then you have this pointer, which I call as adjacent list PTR. Meaning that I go back and where I initially declared my vertex structure, I have here vertex structure declared this place, and then I left that I have one extra field here. So I will say int PQ index. This is what I have extra at new structure. So this field is nothing but PQ index. So this I have added extra. And once I do this, then I can definitely say that now I have got this available. So during my coding for vertex V, I can easily say that I will go to graph V dot PQ index will become the corresponding index to become useful for this. So I can say this will become my new index, or current index, I'll say. And using this index, you can always say, for example, now I say it is current index. So I will get current index used, and then I can say PQ current index dot key will be compared. So wherever we were using a key, I can use this. So just going above in the code, if you remember, here I needed the index. So I'll say, just let me have a different pen so that I'll write with a new word now. So this index becomes effectively nothing but, I will say, current index. Effectively nothing but it is equivalent to saying that graph V dot PQ index. Similarly, here, when I said a decrease key index of V, I have this, and here also key of this to be used. Effectively, it means nothing but the corresponding PQ current index dot key. So this way, I will be able to do this. So this is going to be the overall logic. So I just quickly repeat what we did was, firstly, we have done initialization of your graph array. Then initialize your PQ array. Then what I said was a source based we started. Then what we did was the loop n times, and within this one was extract main operation. Then your adjacency list traversal, and within traversal, if something happens, then we have decreased. So this is the overall logic. Why I am writing again logic is simple. The analysis I am going to do now. So if I talk of analysis part, let's quickly do. Without bothering about O or theta, I will say this step is taking order of V time or theta of V time, but V vertices are there, so I can say order of V. So O and theta I am using interchangeably, so O is always a safer, not an issue at all. PQ, again, PQ has V vertices, so it is set of vertices, it is array of vertices, so this is also order of V. This is going to be order of 1, not an issue at all, source-based something being done. Now, loop n times effectively means order of V. every time extract min being done. So I don't take this order of V separately, because later for adjacents, I will need the aggregate analysis. So I will not bother this nesting. I will say this overall aggregated, how much time it is going to take. Aggregated, this is going to be V times called, and every time extract min. Individual extract min takes order of n or order of log n. In this case, n means number of vertices. Extract min operation over a heap means order of log n, that is order of log v. So v times it will be called, I can say this is going to be order of v log v. Of course, later calls will even have size reducing. So size will keep on reducing, but because we are using O, so this is V log V aggregated. Aggregation, why I'm using? Because aggregated, this adjacent traversal, list traversal, effectively it is meaning nothing but all edges in aggregation. Using this loop, ultimately all edges covered, as in DFS we saw. Ultimately, all edges will be covered, and the totality of this becomes order of E. E times or 2E, because there are double edges undirected, but effectively means order of E. For each call, for each edge, decrease key might get called. And a decrease key is also order of log V, because a decrease key is also heap operation. Heap is of size V, so I have this. So this aggregated will mean order of E log V. E times log V. This will be called E times, because of this particular case. So now I have my total time complexity very clear to me. Let's see here itself. It is order of V plus order of V, step this one, plus order of V log V. And this one has been aggregated here. So it is order of E log V. Combinedly, I can easily say it becomes order of V plus E into log V. Just writing one next slide. So it overall became V plus E into log V. Now, having said that, this becomes one good analysis, but still a better writing can be done. Here also, it is guaranteed that E is going to be greater than equal to V minus 1. I have already said connected graph and MST. So minimum V minus 1 edges are must. Every vertex has to be connected with someone at least. So all vertices except maybe one vertex have to be connected with other someone, means minimum V minus 1 edges. So indirectly, I can say E is greater than equal to V. Then I can automatically say that this I can claim to be order of E log V. If there was no guarantee of E versus V, we couldn't claim this. But because this is guaranteed, I can say time complexity of this is order of E log V. But here assumption is that we used min heap. We used min heap as a PQ. And effectively min heap means it is by default called to be a binary min heap. We have left and right, only 2 children. Actually, there are other bin heaps also available beyond binary bin heap. Beyond binary min heap, something like as Fibonacci heap, etc. So there things will change. But in case of a min heap, your decrease key and extract min take log V time. And that is why you have corresponding operations being considered accordingly and a time complexity being considered. If a min heap or PQ changes, it will change. Like if you go for linear search, as we said that if a PQ index not stored, time complexity will increase. So we have done all this. Having said that, I'll wind up here. I'm sure you will find this very useful and do the implementations. This will help you in an excellent understanding and doing some very good implementation. And with this, it will be so easy, no cramming needed. I'm sure you can all implement without a difficulty. Try it. Next class, you can ask doubts if there are any. Bye-bye. All the best to all of you. Let me just stop recording.